In this video, I'm going to show you how to use the programs for panel regression. I offer two such programs, one that uses generalized linear models and the other that uses GEE modeling. Both programs make use of the R package called Panel R, and because they are so similar in format, I do not make separate videos for them. I can capture the essence of the programs in a single video. I'll highlight the program called GLM Panel Regression first, but after doing so, I'll add some commentary about the GEE Panel Regression program. Okay, let's access the program and get the example data. I'm going to scroll down here to the buttons where the programs are located. I'm going to click on GLM Panel Regression. When I do, a set of instructions appears in the description box, and I'm not going to go through these instructions because I'm going to be showing you how to use the program in this video. A little further down is the input values box where we provide information that tells the program how we want the analysis done. This uses raw data, so I have to go get the data file, and I'm going to click on Choose File, and a browser window is going to open. Here's the file that I'm going to use here, so I'll open that. And these are the variables that are in the data file. Now this list is very important because R is case sensitive, and when we refer to variables in the input values box, we have to respect the capitalization and the exact spelling of those variables. Up here, I'm going to put the full folder path of where the data are located. And I'm going to repeat the name of the data file here. This is so the program will know where to find the data on your hard drive. Okay, before we get into the program, let me provide some background information. Now, panel regression is often used to analyze what are called within-between or between-within models. In RETs, the method is most likely to be used when analyzing the relationship between mediators and outcomes in a limited information estimation framework. Suppose I have two mediators, MA and MB, and a time-varying covariate called COV, C-O-V. I measure each of these variables at the post-test and again at 3, 6, 9, and 12-month intervals during the follow-up period. Thus, I have 5 post-treatment time points to work with for an individual scores on Y, MA, MB, and COV. All can differ for each individual at each time point. Now, there are two types of predictors in panel regression. Time-varying predictors can change in value from one time period to the next, and this is the case for MA, MB, and COV. Here, I have the data for individual 1 just for two variables, Y and MA, and these are the 5 different time points, and you can see that the scores can vary across the different time points. That's also the case for individual 2 and 3 and 4. Time invariant predictors are those that are stable and do not change over time. Examples include for adults how harsh their parents were with them as children, or the age at which they started high school. In our example, I will refer to the time invariant predictors as ZA and ZB. Panel regression often analyzes just time-varying predictors, but it also can incorporate time invariant predictors into the analysis as well. Now, one question I might want to address for my time-varying variables is whether the changes in the mediators across time are associated with changes in the outcome across time. That is, if I work with the data within people, but across time, is variation on the mediator associated with variation in the outcome across the 5 time points. So if I look at individual 1, I can see that I have variation in Y and I have variation in MA, and there does seem to be an association between those. When MA is low, Y is low, and when MA is high, Y is high. And that's also true for individual 2 and individual 3 and individual 4. If I regress the outcome onto the mediator within people, but across time points, Is the resulting regression coefficient non-zero? Panel regression provides perspectives on this question by yielding estimates of such regression coefficients. Suppose I find that the within-person regression coefficient is 0.3. This means that for every 1 unit the mediator changes across time for an individual, the outcome is predicted to increase 0.30 units. Standard panel model analysis is such that it makes the assumption that any variation in this coefficient value in the sample data across different individuals is just random noise, that the value of 0.30 pretty much typifies everyone in the sample. If this is not the case, then specialized analytic methods are required to deal with the coefficient variability, and I'll show you how to implement those later. Now there's a second approach often used in panel regression to estimate the effect of a predictor on the outcome. And this approach emphasizes across individual analysis rather than within individual analysis. Simplifying a bit, I can calculate the mean of the target mediator across the 5 time points for each individual separately, and I also can do the same for the outcome across the 5 time points for each individual separately. So here, I take the average y across these 5 time points and it's equal to 4.0. Here the average value of MA across the 5 time points is 3.0. Same thing for the second individual. I calculate the average of these scores across the time points for y and MA, and I continue to do so for all the individuals in the sample. Now I can regress the mean outcome scores onto the mean mediator scores across all individuals in this study. That is, I can take these scores here and regress them onto these scores here, and I'll end up getting a regression coefficient. That coefficient is referred to as a between-person coefficient because it is calculated across individuals. Now suppose I find that its value is also 0.30. The fact that the two coefficients are similar gives me 2 different perspectives on documenting the effect of the mediator on the outcome. Panel regression also contests the statistical significance of the difference between the 2 types of coefficients in the context of what are often called contextual effects. If the coefficients are meaningfully different, then the question becomes, why is this? Why is the effect different within individuals across time as opposed to across individuals? A classic example of such a contextual effect is the effect of exercising on the occurrence of heart attacks. Across people, those who exercise more are less likely to have heart attacks than those who exercise less, because the former people usually are in better physical condition. Hence, there's a negative association between exercise and the occurrence of heart attacks. However, within a person, heart attacks are more likely to occur when someone is engaging in vigorous exercise. Hence, there's a positive association between the exercising and heart attacks within individuals. Now, with this as background, let's take a look at the GLM program. Before doing so, however, I should note that the GLM panel regression program, as well as the GEE panel regression program, requires that your data be set up in a specialized format, what is commonly known as long format. Here's an example of such formatting for the current data. Note that each individual has a separate time point on a different row. The time point is the variable called wave, and note that the variables ZA and ZB are time invariant, but the other variables are time varying. I have a program on the website called wide-to-long data format that will convert a traditional data file with individuals as rows and variables as columns to long format. So you can use that program to set up the data properly. Okay, back to the input values box here. I have to specify in this first box what the ID variable is in the data, and that would be ID over here. Here I indicate the type of outcome, and the program can analyze continuous data or binary outcomes or count outcomes. And there's a numerical code associated with the different outcomes that appears in the description box. If you need a reminder of those, you can hit the toggle switch down here Turn that off or on, and it'll give you the numerical codes here. So we're going to work with a continuous outcome, which is Gaussian, and so we have the number 1 there. For model type, the program can do either a between-within analysis, or it can do within only, which would only report the within-person coefficients, or between only, which will only report between-person coefficients. And we're going to, in general, be using the between-within. The time variable is called wave. And the core variables are going to be the core variables that I use in the equation that I specify. And those are going to be y, ma, mb, cov, za, and zb. Notice these are comma delimited. I'll explain these other boxes to you in later applications, but for now let's go down and enter the equation. Okay, the equation uses standard R format, kind of, and so I put the outcome first, and then I put a tilde sign instead of an equal sign, and then I list the time varying predictors first. So I'll put MA plus MB plus cov. Then if the model contains time invariant variables, which it does here, ZA and ZB, I put a pipe symbol, which is usually the shift of the backslash on your keyboard. And then I put the time invariant variables. I then hit register input. My program generates the syntax for the program. I copy that to the clipboard. I open up R. Up here in the upper left, I'm going to hit Control V to paste the syntax, and as it pastes, it will execute. The output is in blue and the input is in red. So I'm going to go to the top of the output, and that begins with descriptive statistics. And this gives you descriptive statistics on all the variables in the analysis. Down here, I obtain the results for the model. And this indicates that I'm using a within-between model. It gives me an AIC and a BIC for model fit, and a pseudo R-squared for the fixed effects, and a pseudo R-squared for the total effect. This pseudo R-squared is when we have varying coefficients in the model. This is an index of the interclass correlation coefficient, which is relatively small. Okay, the first thing I get are the within-person coefficients. And this is the coefficient for MA predicting Y, MB predicting Y, and the covariate. So for MA, for every 1 unit that MA increases across time, the outcome Y is predicted to increase by 0.301 units. Here's the standard error, the t-value, the degrees of freedom, and the p-value, which is less than 0.001. Now down here are the between effects, or the across-person effects. And the program has calculated the mean MA, the mean MB, and the mean covariate, and then it has the ZA and ZB, and it basically does a multiple regression, regressing the mean Y onto all of these predictors. I can see, for example, that across individuals, for every 1 unit that MA increases, the mean Y increases by 0.367 units. These are the standard errors, t-values, and p-values associated with those. So across individuals, both the mean MA and the mean MB seem to be associated with the mean Y. And then here are the results for the time invariant covariates that I want to control for. Again, these coefficients are the estimated effect controlling for all other variables in the analysis. Now, if I look at these, the coefficients are fairly similar in the within and the between models. The 0.301, 0.367, 0.297, 0.312. And so that gives me increased confidence in my estimates of the causal coefficients. The intercept terms are treated as random effects, and this just tells me the standard deviation of those. Down here are the confidence intervals for the various effects. So these are the estimates repeated, and then the confidence intervals. And then this reports the correlation between the observed and predicted outcome scores is 0.685. Now the program also does a contextual analysis where it compares the within and between coefficients. So it repeats the within coefficient here, and this is the difference between the within and the between coefficient under the contextual effects. And this difference was not statistically significant. Again, the within effect was 0.301. If I go back up to the between effect, it was 0.366 for MA, and the difference between those is 0.066. And then you've got the contextual effects for MB also. Now this portion of the output shows the predicted Y-score for the first 100 individuals so that you can compare it to the observed Y-score for those 100 individuals. And this is a form of profile analysis that I'll talk about a little bit more later. Down to the end of the analysis. Now over here, I plot the residuals of the model by the fitted values with a smoother. And what we're looking for here is a flat smoother around 0 and basically randomness in the residuals around that smoother. And that suggests that the model is not seriously over-predicting or under-predicting specific parts of the data. All right, let me close this and go back to the input box and make some additional points. Now I can add interactions to the model, and to do so I use standard R format for indicating interactions. So for example, if I wanted to put in an interaction between MA and MB, I would here put in plus MA times MB. You literally put in the product term, and then the program will add that interaction term into the equation. Now, a special case occurs if you're putting in an interaction effect between a time invariant variable and a time varying variable. And that's called a cross-level interaction because the interaction is occurring across different levels. You can specify those interactions, but you have to specify those up in this box up here. So if I have MA times ZB, then it will add that cross-level interaction. And if I also wanted to put in MB times ZB, that would add that cross-level interaction as well. So you have to put the cross-level interactions that you want in your model up in this box, comma delimited. Okay, let's go back and let's put in an interaction, say, between MA and the covariant. Now, it turns out the time-varying product terms can be handled in 3 different ways by the program, and you have to choose the method you want in the interaction demean box that's in the input values box. The best way to calculate product terms in panel models is controversial, and here are the 3 ways that you can do it. A method called demeaning subtracts the mean score of the variable for an individual from the individual's raw score. And here that's done with X and Z, say. And then the product term portion of the model is the 2 component parts plus the raw product minus the mean of that product. And this is a traditional way in which it's been used. The double demean approach works with the centered scores in this way and then also subtracts the mean of the centered scores. And the raw approach follows this particular formulation. Now, the conventional method used in many applications is the demean method. However, research and simulation studies suggest that the double demean method seems to work best in terms of avoiding bias. So this is default in my program and the Panel R program. The decay box here is used if you want to drop some of the earlier time points from your variable that defines the time points. Leaving the box blank means you don't want to drop any of the variables. A value of 0 means you want to drop a time point that has a score of 0. A value of 1 means you want to drop a time point that has a score of 1. Now suppose your very first assessment period is a baseline, and the next assessments are the immediate post-test, the first follow-up, second follow-up, and so on. If I only want to focus on predictors of decay, I might drop that first assessment because it is the baseline. My focus is only on the immediate post-test treatment scores and how they and the mediator simultaneously decay over time. So in this case, because I was only dealing with post-test scores, I just left this blank. But if for some reason you want to eliminate one of the time periods, then you would just put the numerical value associated with the time period here. And if you have 2, you would comma delimit them like this. Now the Show Predicted Y box will show you the predicted Y scores from your model in conjunction with the model predictor values. The entry tells the program how many cases to show. A value of 100 will show the first 100 scores in the input data matrix and their predicted Y values. A value of 200 will show the first 200 scores and so on. This can be useful if sometimes you want to select out certain predictor profile and show what the predicted scores are for those. Now by default, as I said earlier, Panel R treats the intercept for Y for the different cases to be random, so there's no need to specify it as a random effect. The time varying variables are treated as fixed by default. That is, the coefficient value for a given predictor is assumed to be the same for all individuals. But you can loosen this restriction by allowing the coefficient for a given predictor to differ across individuals. Now the way I would do that would be to use this box here. Let's suppose I wanted to make the coefficient for MA be able to vary across individuals. I would do that by entering the following. This says make the coefficient for MA variable across individuals. And this is the variable that you're making it variable across, the ID, the individuals. You put that in parentheses. If you also had a cross-level interaction, you'd put the comma in ZA times MB in, and so on. So in this box you put in the comma delimited cross-level interactions and or the random effects that you want. Now the program also provides 2 types of predicted scores for the profile analyses. Scores that include the random effects and scores that exclude them and focus only on the fixed effects. Former are sometimes referred to as conditional predictions and the latter as marginal predictions. The GEE program only provides one set of predicted scores, namely the marginal predictions. This is because the GEE model does not incorporate random effects into its algorithms. The conditional predictions, which include random effects, give the most accurate reproduction of the scores of individuals in the sample data based on the model. They're person-specific in the sense that they take into account each individual's average response across the random components of the model. The marginal predictions do not use these individualized average responses, but instead use the average response across all individuals, which are thought to represent the typical person in the population as a whole. They tell you that for a hypothetical average person in the population who has a given profile on the fixed effects, what their y-score is expected to be. All right, let me shift over to the GEE program and talk about some differences with it. The GEE panel regression program is much the same as the GLM panel regression program, but there are some important exceptions. It emphasizes marginal effects and does not permit random effects, and it uses a different statistical algorithm for estimating coefficients. In doing so, it makes fewer statistical assumptions. The key differences are highlighted in my book in Chapter 16. One notable difference is that the user must specify a priori a working correlation structure between the outcomes at each time point. The program on my website offers 4 different correlation structures to choose from. Now consider the case of 3 time points. I have a measure of y at time 1, at time 2, and time 3 that I call y1, y2, and y3. The independence model assumes the y are uncorrelated. For panel designs, this typically is not realistic. The exchangeable structure assumes the correlations between all the y's are identical and equal to the value of rho. The first order autoregressive structure assumes the correlations follow a classic autoregressive simplex pattern and is one that is often chosen for longitudinal panel models. See Chapter 16 in my book for detail. The most flexible structure is the unstructured pattern in which the correlations can take any pattern. Simulation studies suggest that the unstructured form is in general a good choice, but it also tends to reduce statistical power and it can lead to convergence issues. For this reason, most methodologists prefer the exchangeable or autoregressive structures for panel data, and usually the autoregressive structure. The output for the GE program is much the same, but you must specify the working correlation structure. The default is a first-order autoregressive structure, which usually is reasonable. With that, the results parallel closely what I went over for the GLM version, but there are no random effects, and the focus is exclusively on marginal effects. Given the length of this video, I won't go over the analysis here, but with what we have already covered is very straightforward. Okay, that's it. Thanks a lot.